Hello students, welcome to this lecture in which we're going to talk about higher order derivatives. So what is it similar to? That is very similar to 2D case with so what is higher order derivatives? Second, third order, but there is a little bit of a problem here with 3D space. So it's similar to 2D case with some complications, right? So what is the complications that we have here? When we have few variables, when we're having multiple variables, so if we have multiple variables, what would be the problem? Let's see what it implies. When we calculate the first derivative, we calculate with respect to x, but then we have a choice whether to calculate second derivative with respect to x or y or z maybe. So there are a lot of choices. So that implies that derivatives can be calculated with respect to various variables. So we have to take this example to practice. Let's take the function which is sine of x to the 5 sorry, I said y, but I meant z. Sine of x to the 5 y squared, and that's our function of x and y. So it's easy to start. We take partial derivative with respect to x. So derivative of sine is cosine of x to the 5 y squared. And then we multiply by the derivative of the inside function according to the chain rule. So we're going to get this expression, which is partial with respect to partial with respect to x. Then if we calculate the partial with respect to y, we're going to get cosine of x to the 5 y squared to x to the 5 y squared. I said y squared, we should decrease the power by 1, so it's going to be y. But then we have a couple of different choices. So for example, we can go over here with a function which is a partial with respect to x, and do it second time with respect to x. So this is going to be d squared f dx squared, if we use notation similar to calculus 1, and usually people write f and put 2 x's on the bottom. So second partial of f. So basically we take this function and we use the product rule. So it's going to be cosine of x to the 5 y squared. Then we'll have 10x to the, looking at the wrong place, gonna get 20x cubed y squared. And that's we took derivative of 2x to the 5y, so then derivative of cosine is negative sine of x to the 5 y squared times 5x times 5x to the 4 y squared, and we still have 5x to the 4y squared. 5x to the 4y squared, unless I made a mistake somewhere. Alright, so we found the partial of x. So partial of x. Right? But we can also do the same with y. We can go and calculate the partial of f with respect to y one more time. So we're going to get f y y sub y y, right? So we take derivative of this function over here. It's going to be cosine of x to the 5 y squared times 10x to times 2x to the 5 plus negative sine of x to the 5 y squared times 2x to the 5y, and we have another 2x to the 5y from the expression. Alright, but also we can go back to the partial with respect to x, but instead of calculating it second time with respect to x, we can calculate it with respect to y. So this will be f sub xy. So we're going back to the top over here. We use the product rule, but we're using y as a variable now, but we fix x. So it's going to be it's going to be a cosine of x to the 5y squared. Now derivative of this function with respect to y, so it's going to be 10x to the 4y. Then we put plus, and then we put derivative of cosine is negative sine of x to the 5y squared times the derivative of this expression inside with respect to y, so it's going to be 2x to the 5y, and we have 5x to the 4th y squared from here. Right, so we calculated this derivative, which is called often cross partials. The second cross partial would be the partial of f with respect to y, but now we're going to take a derivative with respect to x. So we're going back to the to this expression for y, and we take partial with respect to x. So it's going to be what? It's going to be this one. So it's with respect to x, so it's 2 times 5, 10x to the 4y. 10x to the 4, we still have cosine, right? We still have cosine. So it's going to be cosine x to the 5y squared, cosine x to the 5y squared times 10x to the 4 10x to the 4y. All right. Then we put a plus and derivative of this function. So it's negative sine of x to the 5y squared times derivative of this function with respect to x now, with respect to x. So it's going to give us 5x to the 4y squared, and we still had 2x to the 5y. 2x to the 5y. And so we calculated partial in a cross way, right? xy, oh, I forgot to put a notation here, so I should put it here. This is fyx equal to this. But if you look carefully, this term is exactly the same as this term. This term is exactly the same as this term. This one matches up, this one matches up, this one matches up, and this one matches up. All right, so conclusion in our example, fxy is the same as fyx, right? If you have a nice function, that's going to be true. That's going to be true in general. So we can put it as a theorem with no proof. Theorem with no proof. So it has a name, Clairaut's theorem. All right, and the theorem says if the cross partials of z equals to f of xy are continuous, then they are equal. So continuity guarantees that you have a nice function. So in this small lecture, we learned how to calculate partial derivatives in many different ways over the higher orders, and we're going to use them in the future calculations. So probably a good place to stop. That's a nice logical place to stop.